What we are going to begin talking about today is the concept of filter circuits. So, in our discussion of steady-state sinusoidal circuits, we learned that capacitors and inductors exhibited a frequency-dependent impedance, right? So we found that the impedance of a capacitor as a function of omega was expressed as 1 over j omega c, and we found that the impedance of an inductor, ZL, as a function of omega was expressed as j omega L. In a little bit, we are going to use these frequency-dependent relationships to exhibit how capacitors and inductors can be used to either block signals or pass signals in part of a filter circuit. But before we do that, I want to go through and explain what an ideal filter. So before we get into this portion, I want to ask you guys a very generic question. What is the purpose of a filter? To block things you don't want. Absolutely correct. So in all of your vehicles, you have oil filters and air filters and things like that, which are literally their whole purpose is to prevent unwanted particles to reaching sensitive parts of your engine that could potentially cause damage, right? Well, an electrical filter is the same thing. It's a circuit that's used to prevent unwanted signals from propagating further downstream in your system. So ideal filters are simply going to demonstrate the best possible response. Okay, it's obviously practically impossible to build an ideal filter, but I want to talk about ideal filters to give you an example of the 4 types of filters that we are going to be dealing with and to understand kind of exactly what it is that they do. Okay. So these ideal filters are going to exhibit what I'm going to call a brick wall response. What I mean by that is if on our vertical axis, we have the amplitude of our signal, which I'm going to call M for right now. And on the horizontal axis, we have frequency, omega. For our first filter, we're going to have this kind of response. Where for signals having frequency below omega c, all of the signal gets passed to the output of our filter. And for frequencies greater than omega c, none of the signal gets passed. So we can define everything below omega c to be what's called the pass band, and everything above omega c to be called stop band. Since only low frequency signals are being passed, defined by our cutoff frequency omega c, this is what's called a low pass filter. The opposite of a low pass filter is a high pass filter. So in a high pass filter, all signals below a particular frequency are attenuated. And then at our corner or cutoff frequency, we then start to pass signals. So here's our corner frequency. Everything above omega C, go away, is our pass band. And everything below, sorry, is our stop band. All right, so before we address the next two types of filters, I want to talk about these here very briefly. Okay. Low pass filters and high pass filters can be recognized as a first order filter. What I mean specifically by a first order filter is that they only contain a single energy storage element. So we can realize both of these filters with a simple RL circuit or a simple RC circuit, and we can get both responses out of both combinations. Okay. We'll talk about how to do that briefly. Now, the next two filter circuits that I'm going to talk about are effectively combinations of low pass filters and high pass filters. And to get that combined effect, we have to have at a minimum a second order filter or RLC circuit filter to get what's called a pass band, or excuse me, a band pass filter and a band stop or notch filter, okay? So these two can be realized with just RL and RC circuits. They can also be realized by higher order filter circuits as well. But you can do it with just a simple resistor and capacitor or resistor inductor, or you can add multiple energy storage elements and still get the same response, just depending on where you're measuring things at. Okay. All right. So our next circuit, our next response actually, is going to be this guy, which is for a band pass filter. And as the name suggests, there is a certain range of frequencies that will be passed by this filter, while all other frequencies will be rejected. So here in the middle, we have our pass band. And then on either side of the pass band, we have stop bands. Our pass band has two cutoff frequencies, right? Because it cuts off everything below a particular frequency, which we're going to call omega low. And it cuts off everything above a particular frequency, which we're going to call omega high. And then in the middle, we have our center frequency, omega C. Center, yeah. Now, I know that it's a little ambiguous because we're using omega C up here in our low pass filter and high pass filters, where there it's being considered a corner frequency. Mathematically, all these omega C's kind of wind up meaning the same thing, though, okay? So all of these omega C's are going to be where the impedance of our filter is going to be purely real. So that's why I'm using the same subscript for everything, even though it behaves mildly differently depending on things, right? So in our top two examples, low pass and high pass, omega C stands for corner frequency or cutoff frequency, either which. In our band pass filter here at the bottom left, omega C is our center frequency. And then our stop band is defined by two cutoff or corner frequencies, omega low and omega high. And our last type of filter that we are going to be dealing with is the band stop filter. So in a band stop filter, it is effectively exactly the inverse of a band pass filter, meaning that there is a particular frequency range over which all signals get attenuated, and then all other frequencies get passed. So we have a stop band in the middle, which ranges from omega low to omega high and has a particular center frequency. And then we have a pass band that extends from omega low back down to 0, and a second pass band that extends from omega high out to infinity. So these are the four types of filters that we're going to deal with in this class. There are certain filter topologies that you may hear of in your later classes. Like I know for sure in circuits 3, you'll learn about what are called Butterworth filters and Chebyshev filters. Butterworth filters and Chebyshev filters are a particular topology. So they're a particular way to arrange components developed by a guy with the last name of Butterworth and a separate guy by the last name of Chebyshev to realize something approximating these responses. They are typically higher order filters, so third order and higher. So we can't simply look at an RL, RC, or RLC circuit to really understand how they work. So we're not going to talk about them really in this class other than me acknowledging that they exist and then saying we're not quite where we need to be to understand how they behave. Okay. All right, so now let's talk about so a practical filter does not exhibit brick wall responses like ideal filters. Instead, they exhibit a smooth response curve dictated by their transfer function. Okay. So let's talk very briefly about transfer functions here. We're using my favorite generic piece of equipment, the linear black box network. So on the left-hand side is where we will apply our input. And on the right-hand side is where we will measure our output. Since we are dealing with frequency-dependent things, I'm going to express my potential input signals as or frequency domain signals. So we could have an input phasor or an input current phasor. We could have an output voltage phasor or an output current phasor. Our transfer function is simply the output signal divided by the input signal. Okay. So that means technically there are 4 different transfer functions that we could define, right? So we could have a voltage transfer function, V out divided by Vin. We could have a transconductance transfer function, I out divided by Vn. We could have a transresistance transfer function, V out divided by In. Or we could have a current transfer function, I out divided by I. Much like our amplifiers that we dealt with at the beginning of the class, we are going to constrain ourselves to voltage transfer functions, okay? So I'm going to define H of omega as the ratio of V out over Vn. And since V out and Vn are complex numbers, our transfer function H of omega will also be a complex number. Our transfer function really just tells us how our system acts on the input signal to generate the output signal, okay? So let's consider the following circuit. Did I scroll too far? You guys got this? All right. So let's consider the following circuit. Where I have a resistor in series with a capacitor. I'm going to apply my input voltage on the left-hand side, and I'm going to measure my output signal on the right-hand side. And since I'm dealing with frequency domain signals, I'm going to represent my capacitor by its impedance. 1 over j omega c. So what should be a hopefully very straightforward thing here. Our goal is simply to determine the transfer function of this network and then use that information to determine what type of filter we have achieved. Okay, so how do I get my output voltage for this circuit? Voltage division, absolutely. This is a simple voltage divider circuit where our input is applied to the RC network and our output is simply the voltage drop over the capacitor portion. 100% right. So using voltage division, we can see that V out is equal to V in multiplied by 1 over j omega c divided by R plus j omega c. And from this, we have a voltage transfer function, h of omega, that is simply 1 over j omega c divided by R plus. Sorry, that should be 1 over j omega c there, thanks. So this is our transfer function. I hate fractions inside of fractions. So what I typically do in a case like this is I would multiply through by a factor of j omega c over j omega c to clear out those fractions. And so to me, our new transfer function, which I would argue is a more simple form, would be 1 over 1 plus j omega RC. So this is our transfer function. Now, at this point, we might be able to infer what type of filter this is. But I'm going to take this a step further, okay? So that we can really directly see what's happening, all right? So our transfer function here is a complex number in and of itself, right? It is a complex number whose magnitude depends on omega and whose phase angle depends on omega. So I'm going to split this complex number up into those constituent parts. We're going to solve for the magnitude as a function of frequency and the phase angle as a function of frequency, so that we can get the frequency response or the magnitude response and the phase response of the system. Okay? Because both things are frequency dependent. So how do I get the magnitude response? Well, I need to figure out what the magnitude of this complex number is. Now, if you recall from engineering 221, circuits 1, the magnitude of a complex number is simply the square root of the real part squared plus the imaginary part squared. So what I'm going to do now is figure out how to break this transfer function up into a real part and an imaginary part, just using complex number manipulation. Okay. So I'm going to start with our simplified form here, 1 over 1 plus j omega RC. And what I'm going to do is I'm going to multiply by the complex conjugate of the denominator over the complex conjugate of the denominator. So that would look like 1 minus j omega RC over 1 minus j omega RC. And in doing so, I will have 1 minus j omega RC divided by 1 plus omega RC quantity squared. And now I'm going to take this representation and just split it up into parts. So this is going to look like 1 over 1 plus omega RC quantity squared minus j times omega RC over 1 plus omega RC quantity squared. We all okay with the complex math that I've done here? Anything seem particularly wild or crazy? All right, so I've broken our transfer function up into its real and imaginary parts. Now, I know that the magnitude of h of omega is the square root of the real part squared so there's my real part. I'm going to square it, and then I'm going to add to that the square of my imaginary part. So negative omega RC over 1 plus omega RC squared. Square that. And then I take the square root of this whole thing. Let's go through an algebraic step or two here and see what's going to fall out of this, right? So in my denominator, I'm going to expect to see 1 plus omega RC quantity squared, and then that whole quantity squared, right? Because I'm squaring that denominator term, and it's common to both the real part and the imaginary. In my numerator, I'm going to have 1 squared, which is simply 1. And then I'm going to have negative omega RC, that quantity squared. So that'll be plus omega RC squared, like so. And now I have a fraction underneath my square root sign, where I have a numerator, 1 plus omega RC quantity squared. And then I have a denominator that is simply the numerator squared. So from this, I can say that my magnitude response is 1 over the square root of 1 plus omega RC squared. So this is my magnitude response. From this, I can easily determine what type of filter circuit I have. Let me explain about what I mean by that. If I evaluate this response at omega is equal to 0, what do I get? 1. 1 over the square root of 1 is just 1. So what that means is that this circuit passes very low frequencies. What if I were to evaluate this at very high frequencies? So what is the limit of this thing as omega approaches 0? So we're going to have 1 over the square root of 1 plus infinity squared, or 1 over the square root of infinity squared, or 1 over infinity, which is 0. So I have a circuit that passes low frequencies and attenuates high frequencies. What type of filter is this? A low pass filter. Exactly right. So that's how we can determine that. Now it's useful to know what our cutoff or corner frequency is. Okay. So if we plotted this function, so here is the magnitude of h of omega. And here is omega. And this point right here is 1, which is going to be the maximum amplitude, right? Because the largest this fraction can ever be is 1 over 1. What it's going to look like is something like this. Okay. At a very specific frequency, this is going to look like 1 over the square root of 2. That's where our corner frequency is defined. Now, you may be thinking to yourself, why on earth do you care about when this looks like 1 over the square root? So this is when our filter has reached a point that exactly half of the signal power is being attenuated. Now, this is a plot of effectively how our signal voltage behaves, because it's a ratio of volts per volt, right? Signal power is proportional to volts squared, which means 1 over square root of 2 squared is 1/2. So that's why we're looking at this point in particular. It's what tells us on the voltage span of how this is going to behave, where we are rejecting or attenuating exactly half of our signal power. Okay. So to determine our cutoff frequency here, we simply need to know what value of omega makes this function go to 1 over the square root of 2. Well, luckily for us, we've already got a square root sign in the denominator. We've already got a 1 in the numerator, so we don't really have to do a whole heck of a lot of work, right? So if we're trying to make this fraction 1 over the square root of 2, I already have a 1 in the numerator, so I don't need to do any more. I already have a square root sign. This thing inside of here must look like 2, which means omega RC, quantity squared, must look like 1. So from this, omega is simply 1 over RC. The exact same result to me, omega C is 1 over RC, which not coincidentally is the exact same result as the time constant for an RC circuit. So this tells us how we can choose values of R and C to set a specific cutoff rate. Now, one thing that I do want to point out is that this is telling us what our angular frequency, cutoff frequency is. But as engineers, we typically work and measure things using linear frequencies. So our linear frequency cutoff FC, also known as F minus 3 decibels, because whenever a signal power loses 3 decibels, that's exactly when it's lost half of its original power, is 1 over 2 pi RC. So to go from linear frequency to angular frequency is just a factor of 2 pi, like it's always been. Doesn't particularly matter if it's a filter circuit or what. So this is our magnitude response. Our phase response is fairly straightforward as well. So theta as a function of omega is given by the arctangent of the imaginary portion of our transfer function divided by the real portion of our transfer function. The imaginary portion was negative omega RC over 1 plus omega RC quantity squared. And the real part was 1 over 1 plus omega RC quantity squared, which gives us inverse tangent of negative omega RC. So we have taken a simple 2 resistor network and analyzed how it behaves really across all frequencies to provide to us a circuit that is capable of passing low frequency signals and attenuating or blocking high frequency signals. And then went ahead and took it one step further and saw what type of phase change occurs while we're doing this. Okay. So this is our analysis for an RC low pass filter. What I would like to do next is simply switch the order of the resistor and the capacitor and then see what happens. So previously, I took the voltage drop over my capacitor and we observed a low pass filter response. Now we're going to take the voltage drop across the resistor as the output, and what should occur is that we'll observe a high pass frequency response. So what should my transfer function look like? Okay, so I'm not looking for my output voltage here, which would include VN. I want the ratio. We're always going to have a voltage divider circuit. That's what all of these things work out to be. So it's always just going to be the element that we're taking the voltage drop over divided by the total series resistance. Always, always, always. So we're going to cut out that intermediate step because there's no point in doing it if it's always going to work out this way. So that's why I stopped doing one too many steps of easy math. So R over R plus 1 over J omega C. And then I'm going to get rid of my fractions by multiplying through by J omega C over J omega C, leaving me with J omega RC over 1 plus J omega RC. So are we comfortable with this as our transfer function? Let's start there. Any of the two mathematical steps that I took not make sense? All right, nobody is saying anything. We are going to move forward in this example, much like we did the previous one, in as much as we are going to multiply by the complex conjugate of the denominator over the complex conjugate of the denominator, which will allow us to split this function into its real and imaginary parts. So that's 1 minus J omega RC over 1 minus J omega RC. And so what that is going to give me is a denominator of 1 plus omega RC quantity squared. And what the heck just happened? I'm going to write that down again over here because I'm just going to go ahead and split it up into its constituent parts here in one go. Okay. So what's the real part of this product going to be, or what's the numerator? The real part of the numerator. So I have j omega RC times negative j omega RC. So that's negative j squared, which is positive 1. So the real part is going to look like omega RC quantity squared. And the imaginary part is going to look like j omega RC times 1. So j omega RC. I'm going to move the j out to here, and we should have a positive sign. Everybody comfortable with the math we did to split this guy up into its constituent real and imaginary part? All right. So now we are going to take the square root of the real part plus squared plus the imaginary part squared to get our magnitude. So this is going to be omega RC quantity squared over 1 plus omega RC quantity squared. Square this whole thing. So that's my real part squared, my imaginary part squared. I have omega RC over 1 plus omega RC squared. Square this thing. And now we do some simplification here, right? So just as like last time, we are going to have a factor of 1 plus omega RC quantity squared in our denominator, since we had the same denominator for each of our terms, a squared. In the numerator, I'm going to have omega RC quantity to the 4th power plus omega RC quantity to the 2nd power. So I'm going to factor out omega RC to the 2nd power from that, which is going to leave me omega RC squared times 1 plus omega RC squared, like so. Does that track with everybody? Does it make sense? If I multiply through here, I'll have omega RC squared plus omega RC to the 4th power, which is exactly what I would get if I just added those two numerators together. All right, so from here, I can obviously see that my 1 plus omega RC quantity squared bit in the numerator is going to cancel out one of the powers in the denominator, leaving me with omega RC over the square root of 1 plus omega RC quantity squared. If we evaluate this, at 0, what do we get? Zero over square root of 1, which is 0. If we evaluate it at infinity, we wind up getting infinity over infinity, which is 1. And so we have a circuit that attenuates low frequency signals and passes high frequency signals for a high pass filter. So if we were to plot this response, what we would get is something that looks like this. And our corner frequency will once again correspond when our signal strength is exactly equal to 1 over square root of 2, which occurs when omega c is exactly equal to c. And from this, our minus 3 dB or cutoff frequency is 1 over 2 pi RC. All right, so we have pretty, oh, actually, I have to do the phase response. Do that real quick. Theta as a function of omega will be the inverse tangent of the imaginary part. So that was omega RC over 1 plus omega RC quantity squared divided by the real part. Just making sure I'm doing this right. Yep. Omega RC squared over 1 plus omega RC quantity squared, which gives us the inverse tangent of 1 over omega RC. We have, yes. Because we only want the imaginary part. So J is what signifies that it's the imaginary part, but it's not part of the imaginary. So it's the operator that tells us which portion. All right, so as I was saying before, I forgot that we hadn't done this effectively trivial step here. This is really all that I wanted to talk about for today. Okay, so we have developed our methodology for analyzing these circuits, determining their transfer function first, and then using the transfer function to give us the magnitude response and the phase response. What we are going to do on Wednesday is introduce a second energy storage element and see how that meshes. So here's how we realize a low pass filter and a high pass filter. On Wednesday, we're going to talk about the realization of a band pass filter and a band stop filter, and very, very briefly, like literally less than a minute on each, talk about how you can use an RLC circuit to give you a low pass and a high pass filter as well. So you do a second order filter. So we could do an inductor one pretty quickly here. It won't take but a couple of minutes if you guys want to do one. Generally speaking, I would leave that kind of as an exercise to the reader, but I don't mind doing it. If we do have 20 minutes, we can definitely do that. So, Dylan. Yes. It's the same exact thing as Yeah, because if the two elements are in series, then it doesn't matter. Yeah. So Dylan, do you want us to take the voltage drop over the inductor or the resistor? Okay, so the voltage drop over the inductor. So we have a resistor and an inductor. Here's our input voltage, Vn. Our inductor has an impedance of j omega L. And then here is our output voltage, V out. What should our transfer function be? I'm going to let you guys guide me on this. J omega L over R plus J omega L. Absolutely. Conveniently enough, we don't have any fractions that we need to worry about, Connor. Oh yeah, absolutely. So we are going to do what we've done previously, multiply by the complex conjugate of the denominator over the complex conjugate of the denominator. So it'll be R minus J omega L over R minus J omega L. And this is going to give us a denominator of R squared plus omega L squared. So when I multiply the numerator parts together, what's the real part of that going to be? Omega L squared, absolutely. And what's the imaginary part going to be? So omega RL. And then that should be a plus sign there in the middle. If I'm not mistaken. All right. So we have split this up into its real and imaginary parts. So now let's determine our amplitude response, H of omega. So we have our real part, omega L squared over R squared plus omega L squared. We'll square this whole thing. We have our imaginary part, omega RL over R squared plus omega L squared. Square this whole thing. And so what this is going to look like is this. So we're going to have R squared plus omega L squared, quantity squared. In our numerator, I'm going to have omega L to the fourth power plus R squared times omega L squared. I know that I've written that a little oddly, but it's to make it very easy to see that we can just pull out a factor of omega L squared from everything. And so this is going to give us omega L squared times R squared plus omega L squared over R squared plus omega L squared squared, or omega L over the square root of R squared plus omega L squared. So if we evaluate this at 0, we get 0. If we evaluate this at infinity, we get exactly right. My stylus will write for me. And so we can see that this is a high pass filter. All right, so how do we make this look like 1 over square root of 2? So let's play around with some things, okay? Let's say that I have omega L up here, and then I want this down here to look like 1 plus omega L over R. That algebra makes sense? Okay. So if omega is equal to R over L, then this is satisfied. It looks like 1 over square root of 2, right? And our 3 dB frequency is then R over pi L. Our phase response, theta as a function of omega, is equal to the inverse tangent of the imaginary part, which was omega RL over R squared plus omega L squared divided by the real part, which was omega squared L squared over R squared plus omega L squared. So the denominators obviously cancel each other out. That's going to cancel this, that's going to cancel this, and so we have the inverse tangent of R over omega. What do you think will happen if we swap the location of those two elements? We'll have a low pass filter where we'll have the exact same corner frequency, and I believe we'll have the arc tangent of omega L over R. I don't remember whether or not that's supposed to be a negative sign.